Hi, let's continue on the part 4 of our learning unit 6 on the coordination chemistry. Okay, I've talked about complex compound, how you can calculate the oxidation state and how you can determine the coordination number of a complex. And in this part 4, we are going to learn how to name the complex compounds. So complex compounds are usually named using either short name or long name. Short name is written like this. So you have a square bracket here, and then you have the metal. Then in the middle, after the metal, you have to name the anionic ligand first, anionic. So it must be arranged in alphabetical order. And then this is the number of the anionic ligand that you have. It can be either 1, 2, or etc. And then it will then followed by the neutral ligand. And N here can also be 1, 2, or etc. And this neutral ligand also following the rules of anionic ligand, which must be arranged in alphabetical order. So for example, if you have neutral ligand, if you have amine, for example, amine, and then you have chloro. So you must put amine first, only then chloro, because amine has A. Amine starts with A, while chloro starts with C. And then the X here represent the charge of the complexes. So if you have counter ion, you do not have to write the charge of the after the coordination sphere. Okay, for example, this is an example of a complex. So the short name or the short form of this complex is rhenium, RH, which is the metal. And then you have the anionic ligand, which is the methyl. Okay, this is the anionic ligand. And then followed by the neutral ligand here, which is trimethylphosphine. Okay, there are 4 of it here. So it is 4. Now this rhenium is actually +1. And methyl is -1. So your total charge here is 0. That's why you don't see any charge up here. And also counter ion outside of the coordination sphere. And then for this compound, you can see that we write the metal first. And then we have the anionic ligand, which is the chlorine. And then we have the neutral ligand, which is the ammonia here, or we name it as amine. So in this case, so this cobalt is actually 3 plus cobalt. And then this chlorine is 2 minus. So that's why you can see the charge outside of the bracket become plus. Okay. Now let's go to the long name. Normally in the exam, we prefer you to write the long name of the complexes. Okay, only when you encounter, for example, in research, when you write your thesis or you write your publication paper where your molecule is very difficult to be named, so you can use the short form. But normally, in the learning process, like what you did for this course, we usually prefer you to write the long name of the complexes. Okay, how do we do that? Is long name is basically based on Stokes-Warner and IUPAC system. So Stokes-Warner refer more to the naming of the metal, while IUPAC system more to naming on the organic part of the complexes, which is the ligand. So there are important steps or rule in naming this complex compound. Okay, the first rule here is non-ionic compounds, meaning neutral complexes, are given one word name. One word name, meaning you have, for example, tetraamine, dichlorocobalt 2. Okay, and the second rule is pertaining on the ligand. So we have quite a number of rules here, which will be explained in the next slide. Yeah. Okay, rules number 3 for cationic and non-ionic complex, the central atom name remain the same. For example, if you have copper, for example, if it is in cationic and non-ionic complex, the name remain as copper. But if you have anionic complex, the central atom name must end with ate. Instead of copper, it becomes cuprate. Because now we have to change the name to ate. Okay? And then for rules number 5, for polynuclear complexes, I have mentioned before what is polynuclear complexes is where you have one or more than two metal inside the molecular structure of a complex. And normally for polynuclear complex, they contain bridging ligand, which must be indicated by prefix mu. So if you have more than one bridge group, you must use Latin prefix dimu, trimu, or etc. Okay, now let's take a look on the second rule pertaining on ligand. So the first rule here is ligand is named first, followed by metal center. Like what you have seen in the previous example. For example, if you have nickel and NH3 4 NH3 like this. Okay. Then 2 plus here. Okay. You name the ligand first, meaning this is amine, special name amine. And then you have 4 amine, meaning it is tetraamine. And then after that, because this is a cationic complex, so the name is still nickel. And then you have the oxidation state in the middle. After that, because it is an ionic complex, so you need to put ion at the end of the name. Okay, then we have another rules, which is ligands are named by following the alphabetical order. For example, if you have nickel like this, you have 1 chlorine, and you have 3 ammonia. For example, now it become plus because the nickel is 2 plus, chlorine is minus 1. So in this case, you name the chlorine first, meaning chloro tetraamine nickel 2 ion. Okay, now we have rules number 2.3, which is anionic ligand name ending O. Okay, I will explain this on the next slide. And then 2.4, neutral ligand must be named same as the molecule name, no special ending. Okay, and this also will be explained further on the next slide. And also another type of ligand, which is the positive ligand, which the name will end with IU. This one will also be explained in the next slide. After that, there are two more complicated rules, which is 2.6. If you have more than one ligand, you must have Latin prefixes. For example, di, tri, tetra, etc. For example, like this just now, if you have 4 ammonia, it becomes tetraamine. Okay, now for 2.7 rules. So if ligand is polydented, you must use Greek prefixes, bis, tris, or tetrakis. For example, if you have ethylene diamine. Ethylene diamine is a bidentate ligand. The EN is a bidentate ligand, and its name contains Latin prefixes, which is di, ethylene diamine. So if you have two EN, for example, you must have Greek prefixes bis ethylene diamine. I will explain this further later on. Okay, let's go to rule number 2.3, which rules pertaining the negative ligands. Okay, when we talk about negative ligands, we know that anionic ligands are also called negative ligands, and this name of negative ligands usually end in O. For example, if you have a ligand, the end of the ligand is ITE, it must be replaced by ITO. So if you have IDE, it must be replaced by just O. And if you have ATE, it will be replaced by ATO. Okay, for example, if you have chloride ion like this, chloride ion, so this IED is now changed to O. So instead of chloride, it now become chloro. And then we have Cn minus here. It is actually cyanide. And now because it has IDE, it is now changed to cyano. And then another one, which is sulfate, because we have ATE here, ATE, so you change it to sulfato. Okay, now we have NCS, NCS minus, which is isothiocyanate. It is now changed to isothiocyanato. Then if you have thiocyanate, it is changed to thiocyanato. And if you have nitride like this, because IDE, it is changed to O, so it is become nitro. And if you have nitrite, it is now changed to nitrito. And if you have carbonate, it is now changed to carbonato. Okay, next we go to the rules number 2.4, which is the neutral ligands. So neutral ligands, they are named the same as the molecules, except for a few which have special names. For example, water molecules, the special name of this is aqua. And we have ammonia molecules, which named as amine. And you must note that it has 2M representing their special name. And then if we have NO, it is nitrosyl. And if we have CO, it is carbonyl. And then if we have this bidentate ligand, which is called as ethylene diamine. Okay, and then neutral ligands, they have no special ending. We just follow the same name as the molecules. And normally neutral ligands are made up of organic groups. This is also an example of a neutral ligand, which is a benzene group, but one of the carbon is replaced by the nitrogen, so this is called pyridine. And then there is also an example here when you have phosphorus attached to 3 benzene groups, so this is called triphenyl phosphine. Okay, so in terms of positive ligands, normally the name ends in IU. For example, if you have this positive ligand, then this is actually a hydrazine. But because it has positive charge, it becomes hydrazinium. For rules 2.6, the name of each ligand is normally preceded by a Latin prefix, for example di, tri, tetra, penta, and hexa, and also etc. If it depends on the number of the ligands, and if it is more than one of that ligand is bonded to the central atom. Okay, if you look at the example here, the first example is the platinum complexes. So you can see there are 4 chlorine ligand in here. So these ligands are named as tetrachloro. While for the second example, you can see that in these cobalt complexes, there are 4 amine group here, and then there are 2 chloro. So the ligands are named as tetraamine dichloro. So what I want you to notice that amine should be named first because it is A, while chloro should be named as the second one because it starts with C. But then the Latin prefixes tetra and di does not influence the alphabetical order. Your alphabetical order starts with the name of the ligand. Okay, now let's look at the another rule, which is rule 2.7. So if you have polydented ligand, polydented meaning a ligand that have more than one donor. For example, ethylene diamine. So the number of ligands bonded to the central metal atoms is normally indicated by corresponding Greek prefixes. For example, if you have 2 ethylene diamine, you should name it as bis ethylene diamine. If you have 3 ethylene diamine in your structure, it is tris ethylene diamine. And then if you have 4 tetrakis, 5 pentakis, 6 hexakis, and etc. Okay, if you look at the example here, in this complex, you have 3 ethylene diamine ligand. So when you have 3 ethylene diamine ligand, so these ligands are named as tris ethylene diamine. In another situation, Greek prefix is also used when Latin prefix forms a part of the name of the ligand. For example, if you have triethylamine, in this case, N is the donor atom, and this nitrogen is attached to 3-methyl group. And then you can see that triethylamine. In this case, the ligand name is enclosed in parentheses. Parenthesis meaning bracket like this. So ligand in this complex are named as tetrakis triethylamine because you have four triethylamine ligand in this complex. Another rule is if you have a cationic complex ion. Cationic meaning, for example, you have this is your metal, this is your ligand. Okay, you have 4 neutral ligands, for example, and then you have another neutral ligand, 2, and then you can see that this is 2 plus, for example. Okay, this is what we call as cationic complex ion. So you have charge 2 plus outside of the bracket. Or you can have a neutral compound or a non-ionic compound. For example, L4. Then you have another L, which is 2. And then you have chlorine ion outside. Okay, this is non-ionic compound. So neutral complexes, the central atom is given its ordinary name, which then followed by its oxidation state and Roman numeral enclosed in parentheses. Parentheses means bracket, yeah? Okay, if you look at the example here, this is the first example. You have the chromium complexes, which contain water ligand and chlorine ligand. So, since it has 2 plus charge outside of the bracket, so the name of the central metal atom remain the same. Okay, in this case, you have 5 water molecules. So it is pentaaqua. Then 1 chlorine, chloro. Then you have chromium metal here. So it is chromium. And then you calculate the oxidation state of the chromium. And then it is 3. But because it has charge outside of the bracket, it is called ion. So another example is when you have neutral complexes. Neutral complex. So in this chromium complex, you have 3 amine ligand and 3 chloro ligand. So the complex is named as triamine. trichlorochromium 3. You notice that there is no ion at the back here because this complex is neutral. There are no charge outside of the bracket. For anionic complex ion or negative charge complex, the suffix ate is added to the name of the central atom followed by the oxidation number in Roman numerals which enclosed in parentheses. Okay, if you look at the example here, this is one example of an anionic complexes where you can see that outside the square bracket there is a negative charge stated here. Okay, so in this case, when you want to name the complex, it starts with the ligand name, and then you have 6 ligands here, 6 cyano, so it is hexacyano, and then since this is chromium, but it is anionic complex, you change chromium to chromate. And then you have, when you calculate the oxidation state, so the oxidation state of this chromium ion is 3 plus, so it is as called 3 here, it's written as 3 here. And then since you have charge outside of the bracket, so you need to put ion in the name. Okay, let's say if you have another example, which is you have, instead of 3 minus, you have 3K outside of the bracket. Okay, we are using the same example. Okay, in this case, how do you name the compound? How do you name this complex? Is you need to name the counter ion first. This is also the counter ion because it is situated outside of the bracket. So in this case, you have to add another one, which is potassium. So make sure potassium has space, yeah, has space before this name, hexacyano, and then since your counter ion is positive, so meaning that your complex is actually negative, so you still have to name the central metal atom as chromate 3 ion, no longer ion, but it has been replaced by the potassium. Okay, so if you have different type of metal, for example, if you have tungsten, so this W, its name is tungsten, become tungstate. If you have molybdenum, it become molybdate. So if you have platinum, it become platinate. If you have nickel, it become nickelate. So if you have plumbum, it is plumbate. And then if you have silver, it is argentate. So if you have aluminium, it becomes aluminate. Okay, for polynuclear complexes, I hope you still recall what is polynuclear complexes. It is complexes that contain more than one metal in the structure. So these polynuclear complexes, they are usually connected by bridging ligand, which often indicated by prefix mu. So if there are 2 or more bridging groups of the same kind, it is usually indicated by dimu or trimu. Let's say if you have a complex, you have 2 chlorine that serve as a bridge, as a bridge ligand for metal, for example. And this metal has another ligand attached to it, for example. So when you name this, you have 2 chloro here. So meaning that you have di-mu-chloro, like that. And then bridging group are normally listed alphabetically with the other group unless the symmetry of the molecule allow a simple name. And then if the bridging group bridge more than 2 metal atoms, it is shown as mu3, mu4, or etc. to indicate how many metal atoms it is bridging. So for bridging ligands or polynuclear complexes, there are 2 types in which The first type is when you have both sides of the complexes are symmetrical, and the second one is when you have a molecule that is not symmetrical. So I'll show you how to name this complex at the next slide. For symmetrical polynuclear complexes, so these are the example of how we can name them. Okay, the first example here you have, if you look at the first example, we have two units here. Okay, these two units, they are the same. So that is what I mean by symmetrical. So between these two complexes, you will see another ligand here in the middle. So this is what we call as bridging ligand. So in this case, how do we name it? We first name the bridging ligand first. So it is indicated by mu, and O2 is called peroxo. And then if you look at one unit here, it is pentaamine cobalt 3. But what does it mean by bis here is when you have two sets of this yellow highlighted unit. So that's why you need to put bis pentaamine cobalt 3. And then if you notice that you have charge outside of the bracket, so you need to put ion. Okay, for example number 2, you can see that there are two ferrum ion here. Okay, so if you look at the complexes, it has the same unit, left and right. So at the left hand side here, you will see 3 carbonyl and 1 ferrum. And at the right hand side, you can see 1 ferrum and also 3 carbonyl. So in this case, you look at the middle. So this middle is the bridging ligand. And you see that you have 3 bridging ligand here. So how do we name this? We first we name the bridging ligand. So since you have 3 bridging ligand here, so it is tri, mu, and then CO is carbonyl, and then you have bis because you have two sets of this yellow highlighted unit, and then so the unit is named as tricarbonyl, and then iron 0. Why it is 0? Because cobalt is 0, it's a neutral, and then this is also 0. So this is also 0, so everything is 0, so iron is 0. Okay, let's take a look at how we can name the unsymmetrical complexes. Okay, what does it mean by unsymmetrical complexes? Is when you have two sides are not the same. Okay, if you look at the side here, okay, this is the first side. Okay, so this is the second side. So their ligands are not the same. But you know there is a bridge in the middle between the two metal here. So this is the bridge. Okay, so how do we name this? Is we name this side first. You remember, because it is unsymmetrical, you cannot name the bridging ligand first. You need to name the first side here. So it is pentaamine cobalt 3. Then you have mu dash mu, and this molecule is called amido, mu amido, and then you have triamine, then diaqua, and then cobalt 3. This chloride is this one, the counter ion, so chloride. Okay, how do you know the charge of the metal, or how do you know the oxidation state of the metal? So in this case, when we calculate, you know that since we have Cl5 outside, meaning this is plus 5, right? So plus 5, H2O is 0. So NH3 is 0. And then NH2, amido here is minus 1. Okay. When we take a look at these complexes, so you have 5 here. And then the inside only have minus 1. It means that you need to have 6 here. 6 minus total charge of the metal is 6 minus 1 equals to 5. And you have 2 cobalt, 6 minus 2. So this is 6 divided by 2. So this is 3 and this one is 3. That's why it is cobalt 3. Okay, let's look at another example. Okay, in this case, you also have different side. Okay, this is the first side, and another one is the right side. Okay, you have two bridge here, O2 and OH. Okay, in this case, we name the first side first. So it is tetraamine, cobalt. Okay, leave this one first. And then we have mu. It is hydroxo. And then mu peroxo. Okay, this is peroxo. Okay, please take note that even if you name the bridging ligand, it should be in alphabetical order. Doesn't matter if the peroxo is up or H is down, but you still need to name the hydroxo first because it is H. Then followed by P. After that, you name the second unit, which is, you can see there are two amine, so diamine, and then 2 chloro, dichloro, cobalt, and chloride. Okay, so how do you know they are cobalt 3? Okay, in this case, this one is minus 1, this is minus 1, okay, this is minus 2. Okay, so since you have two chlorine ion outside, meaning that the charge after the bracket is actually 2 plus. So how do you get 2 plus from minus 4 here? Means it is 6 minus 4 equals to 2. Okay, so you get the 6 divided by 2 cobalt. So it is 3. So this cobalt is 3. This cobalt is also 3. Okay, with this example, so this is the end of our part 4. Then I will continue part 5 on crystal field theory in the next video. Thank you.